my name is Dave Williams, and today we're talking about the new IPEM PiHat, the mains energy monitoring board that's been launched on Kickstarter for a Raspberry Pi. So this is the pre-production version of the board, and then behind it we have the IPEM PiHat Lite, which is the light version of the main board. So come back to the main board. We have the Atmel, originally ATM90E36A energy monitoring chip. On the right we've got 4 inputs, 1, 2, 3 and neutral, which allows us to do single phases, split phases, dual phase, 3 phase, star and delta configurations, so plenty of scope there for mains monitoring. On the left we have our DAC output from an MCP4728, which is a 12-bit DAC. On the left here at the bottom we've got our ADC inputs, 4 channels going into an ADS1115, which could be 4 single inputs or 2 differentials to a 16-bit DAC. We've got dual isolated relay outputs. Up here we've got a PCA9671 GPIO expander, which is controlling the chip and also the GPIO on the Pi connections. We've got a TMP102, which is a temperature sensor, digital temperature sensor. Over here we've got the 24C64, which is an EEPROM, which allows us to store configurations, log data, etc. if we so wish. And on the reverse we've got a real-time clock, the DS3231 accurate real-time clock, complete with real-time clock battery connection should you wish to have battery backup. The light version essentially is the 90E36 chip with our 4 inputs and Type-C power input. And the reason for this is it enables the boards to be stacked and powered in a number of different configurations if you so wish, and controlled by the PCA9671 GPIO expander. So it allows us, in technically speaking, to have 64 of these boards stacked. In the real world that wouldn't be necessarily practical, but the features are there and allows us to change configurations. And actually, whilst we're talking about configurations, we've got 3 rows of dip switches. So the rows on the right here are for the inputs, so it enables us to select whether it's a current CT clamp, the generic ones, or a Rogolski current transformer. So both inputs can be provided. In the middle we've got configurations for the 90E36 for DMA control, etc. Split phase as well, and single phase. And then on the left we've got the configuration for the GPIO expander to select one of 64 I2C addresses. So it's quite a compact little board, but it's looking really good and it's working really well as well. And also, actually, whilst I'm here, there's some status LEDs from both the ATM chip relays, also from the power status, and the press button is just a user input button should you wish to make use of it. Over here, this is an IPEM PiHat Lite connected to a Raspberry Pi 5, and what's happening is we're currently testing the GPIO expander and checking its stackability, and that's looking really good at the moment, and on different flavors of the Raspberry Pi, the old 3, the 4, the 0, etc. just to make sure that it all works as it should do, and it's looking really good at the moment. This is just some scripts that have been run just to check that the expander performs. In addition to a host of hardware and software being completed on the Raspberry Pi on the adjacent bench, because the board itself is controlled via SPI and I2C, it lends itself to being controlled by a host of other MCU processors such as the microchip PIC, AVR, Cortex, Renesys, NXP, the STM32, and of course the range of expressive MCUs. Now, the original IPEM board, which we have over here, was controlled by the ESP32. So what I've done is made a little interposer, which is effectively an ESP32 with a Pi header, and we have this. Now the reason for putting this together was the fact that I've got a host of testing software that I produced for the original IPEM based on the ESP32. And that then was merged into the Flix software, which is available for the original IPEM. So I sort of modified it slightly, and then adding the control for the DAC, the MCP4728, the ADC A115, the TMP102 temperature controller, the real-time clock, the DS3231, and the GPIO expander, the PCA9671, and then that enables me then to test the board on my test set. So if we turn the test set on and give it some power, we then see our calibrated resistive loads showing 340 watts, 246, 247 volts. And remember, the voltage is being produced via a transformer for safety, so we've got low voltage AC coming into the board. We see our 90E36, the ATM status LEDs flickering away, and that's all working really nicely. Now the reason for that is I'm unable to test both the current clamps, which are standard current clamps, CT clamps, and also the Rigolsky. So here we have a Rigolsky clamp, and the inputs to the board are controlled via the dip switches, so we can select either CT clamps, which is a 3.5mm jack sockets, or the Rigolsky, which are the little 2-pin headers on the side, and the dip switches then select one or the other for each of the channels independently. Now that enables the testing for sort of single phase, multiple single phase circuits, dual phase, so it's 2 lives, for example, in the USA, which is split phase, 3 phase star, which is 3 live and a neutral, and a 3 phase delta, which is 3 lives. So it's a whole host of testing then can be completed and enables the board to be used in the field, whether at home, office, industry, solar farms, etc. And so we'll turn the loads back on again, and we've got our readings on the display. Such. Now turn those off for a moment. So the interface, so I've got one around here somewhere. It seems to have walked. It's always the way, isn't it? And moving around to the side, we've got our DAC output and ADC inputs. Now these are using the standard JST SH 1mm 6-pin connectors. Both connectors have got 0 and 3v3, and then the 4 channels. So the DAC output will give us our 4 channel outputs from the DAC, and the ADC input will give us our 4 singles inputs, or 2 differentials, depending on what you would like to use them for. The relays outputs are normally open, normally closed, and there's 2 independent controls. And then we've got our TMP102, which is a temperature sensor, and PCA9671, which is the GPIO expander. The GPIO expander is essentially the same as a PCF 8575 or an MCP 23017. The advantage to the PCA 9671, which I've used, is that it allows up to 64 I2C addresses, and this is where the stacking of the boards are made quite unique and enables the boards to be used in a number of situations where you've got 3, 6, 12 upwards channels that you'd like to be able to monitor. In the real world, 64 boards is quite a lot, but certainly there are instances where we would want to have 4, 8 or maybe even 12 boards stacked. The real-time clock battery is a standard Raspberry Pi 5 connector, and this is the 2032 cell, button cell, that just plugs into the side there. So there we have it. Thank you for watching.
Okay.